Okay, hello everyone. I'm Professor Jin-uk Lee from Seongkyungan University. First of all, I would like to thanks to Professor Il Jeon for giving me a valuable chance to invite to the lecture here. Today, I prepare a lecture for comprehensive understanding of perovskite solar cells. So the purpose of this lecture is to understand the history, structure, and basic operation principles of the perovskite solar cells. So you can refer to the outline for this lecture. Perovskite is kind of a crystal structure. You may already heard of the oxide perovskite. In fact, the oxide perovskite was first developed before the halide perovskite was discovered. The oxide perovskite was first discovered by the Russian mineralogist in the Ural Mountain in 1839. This crystal was named after Russian mineralogist L.A. Perovsky, who served as a Minister of Internal Affairs under Nicholas I of Russia previously. Followed by the discovery of the oxide perovskite. In fact, the halide perovskite was synthesized much later than the oxide perovskite. Especially the organic-inorganic hybrid perovskite, which is nowadays commonly used for the perovskite solar cell, was first synthesized in 1978 by the German scientist. At that time, he just reported the basic crystal structure and properties of this halide perovskite. You can see that he introduced the methylammonium tin bromide or tin iodide perovskite. And in this paper, he introduced the methylammonium lead halide perovskite materials. And in 1999, scientists has focused on the utilization of the organic-inorganic hybrid perovskite for the development of the electronic device. In this device, they use the two-dimensional organic-inorganic hybrid perovskite, which has the excellent in-plane charge carrier mobility. So they incorporate this perovskite into the transistor device. You can see that this paper, based on the organic-inorganic hybrid perovskite material, was published in the science paper. The perovskite material used for photovoltaic device is based on the three-dimensional perovskite material, which has a formula of ABX3. Here, the A is the monovalent cation, such as the methylammonium cation, or formamidinium cation, or cesium cation. This A cation occupy the cubo-octahedral site of the unit cell, and this A cation is surrounded by BX octahedral, which is correspond to here in two-dimensional view of the crystal. B site is occupied by divalent cation such as lead 2 plus or tin 2 plus, whereas X site is occupied by the halide anion such as iodide, bromide, or chloride. For understanding of the physical chemical property of this perovskite material, we should know the chemical bonding properties of the perovskite material. In contrast to the conventional silicon material, which consists of covalent bond, this perovskite material consists of ionic bond, and the lattice has the soft and polarizable nature. Based on the absorption coefficient of the material. Here, there is the two perovskite material based on the methylammonium cation. You can see that their absorption coefficient here is much higher compared to the silicon material, which means that it may be consist of direct band gap in contrast to the indirect band gap of the silicon. So this chart summarizes the properties of the materials. You can see that the perovskite material has the direct band gap. The typical perovskite material used for high efficiency device has the band gap of around 1.5, and it is tunable by tuning the composition of the perovskite materials. And compared to the other material, which was fabricated at very high temperature, perovskite material can be fabricated at relatively lower temperature, and it can be processed under nitrogen or dry air atmosphere. So because of the much lower temperature and the ambient atmosphere, in contrast to the very high temperature and vacuum atmosphere used for the conventional inorganic material, this advantage provide the lower cost of the process for the fabricating the perovskite film. And you can see that absorption coefficient is much higher than the silicon, which is the indirect band gap material. And due to the higher absorption coefficient, of course, we can use much thinner films for making high efficiency device. And the carrier mobility is lower than silicon, but is comparable with the conventional CIGS material. And but the carrier lifetime, you can see that is much higher than the CIGS material, which is due to the characteristic property of the halide perovskite. I will introduce the property in later slide. And owing to the very long charge carrier lifetime, you can see that diffusion length is very long compared to the CIGS material and the gallium arsenide material. And right now, the reported certified record efficiency is 25.2%. You can see that the efficiency is almost close to the silicon and already higher than the CIGS solar cells. But in fact, still for the perovskite material, there is issue of the large area fabrication, because this efficiency is only based on the small area cells. Right now, still the large area module efficiency is still lower than 20%. And this figure shows the evolution of device structure for the perovskite solar cells. You can see that from 2012, the device structure of the perovskite solar cell has been evolved to the different structure, which is owing to the study on the properties of the perovskite material, which will be introduced from now on. For understanding this first structure, we should understand the history of the perovskite solar cells. You can see that this device structure resembles the dye-sensitized solar cells. It is because the development of this perovskite solar cell was originated from the dye-sensitized solar cells, where it used the mesoscopic titanium dioxide and absorbed the organic molecular dye, which absorbed the absorption, and the photo-generated electron is injected to the TiO2, whereas the remaining hole is regenerated by the redox couple. And as you know, the molecular dye, the density of state of the molecular dye should be much lower than the crystalline solid material, because in the molecular dye, we don't have much atoms to constitute the molecular orbital. So there, the density of the state should be low. And then, in fact, in the molecular dye, the energy state is discrete. So the absorption coefficient should be much lower than the crystalline solid material. So it is difficult to achieve very high light harvesting efficiency. So the researcher tried to replace the molecular dye with the semiconductor crystal. In contrast to the molecular dye, the semiconductor crystal should have a much higher absorption coefficient, because it is consists of much larger number of the atoms in the crystal, and it should have a broader absorption range, because the energy state should constitute the energy band. So it should have much broader absorption range, and it should have much better charge transporting capability, because the charge transporting mechanism in the organic material should be based on the hopping of the charge. So the mobility of the charge in the organic material should be relatively lower than the mobility of the charge in the inorganic material, where the charge is transferred through the energy band. And based on these properties, the Professor Tom Miyasaka, who is a Japanese chemist, tried to incorporate this perovskite material into the dye-sensitized solar cells. So this is the first paper reporting the perovskite solar cells, which was published in JACS. You can see that he formed very small perovskite crystal on the surface of titanium dioxide by solution process. And you can see that the sensitizer, the term sensitizer is because of it is based on the dye-sensitized solar cells. So he still used the term sensitizer, perovskite sensitizer. He utilized the two different perovskite material, which is the methylammonium lead bromide and the methylammonium lead iodide. And he was able to achieve the efficiency as high as 3%. But as you can see in the figure, this is the graph. Shows the EQE of the device. The EQE of the device is much lower than the 100%, which means that the light harvesting efficiency or charge collection efficiency is not high enough to achieve the higher efficiency. Inspired from this study, Professor Namgyuk Park in our university tried to utilize the perovskite material into the sensitizer solar cells. So he used the term quantum dot, which means that the perovskite material is formed as a nanocrystal on the surface of the titanium dioxide. And in this study, you can see that he enhanced the concentration of solution used for fabrication of the perovskite on the surface of titanium dioxide. As you can see that the color of the perovskite sensitized film become much darker as the concentration of the solution increased. And based on the high concentration perovskite solution, he was able to enhance the light harvesting efficiency of the perovskite sensitized titanium dioxide, which enhanced the external quantum efficiency of the device up to 80%. And owing to the higher external quantum efficiency, he was able to achieve the efficiency as high as 6.5%. So this is the second paper reporting the solar cells based on the perovskite materials. But in fact, both the Professor Tom Miyasaka and Professor Namgyuk Park utilized the solution electrolyte for whole transporting layer. But as I mentioned in the previous slide, the perovskite material consists of ionic bonding, which means that it can be easily dissolved in the polar solvent. For the electrolyte, it is typically consists of the polar solvent, such as the acetonitrile. So it can easily dissolve the perovskite materials on the surface of the titanium dioxide nanoparticles. So you can see that without injection of electrolyte into the device, the color of the sensitized titanium dioxide layer is very dark, but as we inject the electrolyte into the device, it starts to dissolve the perovskite nanocrystal on the surface of titanium dioxide, and as the time goes by, it starts to completely dissolve the perovskite crystal on the surface of titanium dioxide. So this phenomena is due to the ionic bonding in the perovskite lattice, which is vulnerable to the polar solvent. And to resolve this very poor stability issue, Professor Namgyu Park replaced the solution electrolyte with a solid-state Hall transporting material. This study was published in 2012, and you can see that the first perovskite solar cell based on the solution electrolyte was first published in 2009. For 3 years, there was almost no research except for the paper by Professor Namgyu Park regarding the perovskite solar cell, because it is due to very poor stability based on the solution electrolyte. Because the device is completely degraded within few minutes, so it is very difficult to further study on the perovskite solar cells. And 2012, Professor Namgyu Park finally replaced the solution electrolyte with a solid-state Hall transporting material. So in this device, he utilized the spiroamyotad, which is the organic Hall transporting material. So you can see that still it used the mesoporous titanium dioxide sensitized with the perovskite nanocrystal, and on top of the titanium dioxide layer, the Hall transporting spiroamyotad was deposited, and this spiroamyotad infiltrate into the mesoporous titanium dioxide layer and served as a Hall transporting layer. So in this structure, electron is transported through the titanium dioxide, whereas the Hall is transported through the Hall transporting spiroamyotad. And you can see that under one-sun illumination, they achieved the efficiency as high as 9.7%. And because we replaced the solution electrolyte with the solid-state Hall transporting material, you can see that the device efficiency can maintain up to 500 hours without any degradation. And shortly after his paper published, the similar study was published by the English scientist Professor Henry Snaith. The paper published in Science Journal, which report the solid-state perovskite solar cells based on the meso-superstructured structure. In this study, he still utilized the solid-state Hall transporting material, spiroamyotad, but instead of titanium dioxide, he used the aluminum oxide, which is the insulating oxide. In fact, in case of titanium dioxide, it is anti-semiconducting oxide, so the photo-generated electron in perovskite will be injected to the titanium dioxide and collected towards the electrode. Whereas in case of aluminum oxide, it has much higher band gap. So the photo-generated charge cannot be injected to the aluminum oxide. So although he used the aluminum oxide, which is the insulating material, he insists that perovskite itself has the capability to transport the charge through its crystal layer. So charge can be transported through the perovskite layer to the electrolyte, to the electrode. And you can see that he achieved the efficiency as high as 10.9%. And because of the charge transporting property, he shows that the device voltage, open circuit voltage of the device can be enhanced by using aluminum oxide. It is because the if we inject the photo-generated electron to the conduction band of the titanium dioxide, there should be some loss of the potential. But for the case of aluminum oxide, it does not accept the electron from the perovskite, so there should be no potential loss, which will lead to enhancement of the open circuit voltage. And importantly, in this paper, he shows that just planar structure can also work, although the efficiency of the device was much lower than the device based on the mesoporous oxide layer. So you can see that first the development of the perovskite solar cell was based on the dye-sensitized solar cells. So it first incorporate the sensitized system for collection of the charge from the device. And then Professor Henry Snaith shows that perovskite itself can transport the charge. So although we use the insulating aluminum oxide, charge can transport through the perovskite layer. And then from this study, people found that the perovskite itself can transport the charge. So later, the mesoscopic system and the planar heterojunction system was developed, where the charge is transported through the perovskite layer. So both the electron and hole should transport through the perovskite layer. So the charge transporting property of the perovskite layer should be very good in this device structure. So in 2013, there was several studies to investigate the charge transporting property of the perovskite itself. So they used the photophysical measurement to characterize the charge transporting capability of the perovskite material. So they found that the electron and hole diffusion lengths can both close to the 100 nanometer. And from the photophysical measurement, they found that the exciton binding energy of the charge in the polycrystalline perovskite film is just a few tenths of the milli-electron volt, which means that at room temperature, almost all the photo-generated charge is dissociated to form the free carrier. So the charge transporting mechanism should be different from the organic material. And the charge carrier diffusion length was measured to be the 100 to 1000 nanometer, depending on the composition of the material. And even for the single crystal, the diffusion length as high as 200 micrometer was measured. So, which means that because the typical film thickness for the perovskite material for the device fabrication is 500 nanometer to 1 micron. So the diffusion length for both electron and hole should be enough to reach the each electrode. And based on the photophysical measurement, the charge carrier dynamics was also studied. The charge carrier concentration follows this equation, where the constant A is related to the trapping of the charge, and the constant B is time constant for radiative recombination, and the constant C is the Auger recombination. So in this graph, they summarize the constant for the perovskite material. So you can see that for trapping rate, it is typically at the scale of 10 to the 6 per second, whereas the radiative recombination is 10 to the minus 10 cubic centimeter per second, and the Auger recombination is 10 to the minus 28 square of cubic centimeter per second. So we can calculate the tentative radiative efficiency of the perovskite film by using this constant, because the only B radiative recombination will contribute the radiative property of the film. So we can calculate the radiative efficiency by using this equation. So this graph is calculated by using this equation. So based on this understanding of the material property, people tried different kind of device structure. So in this structure, they used the mesoscopic device structure, where the perovskite is still deposited on the titanium dioxide layer, but it forms the thin capping layer on top of the mesoporous layer. So as you see in this structure, perovskite can transport both through the titanium dioxide layer as well as the perovskite crystal itself. And also for the hole, it should transport through the perovskite layer to reach at the hole transporting layer. And based on this device structure, they were able to achieve the device efficiency as high as 15%. In fact, in this study, they first certify their device by the National Renewable Energy Laboratory in US. So there is the first dot on the record efficiency chart, which is from the this study by Professor Michael Gratchel. And later, Professor Henry Snaith reported the just planar heterojunction structure, where the perovskite layer was formed by the dual source evaporation. Typically, by using just bare solution process, it is difficult to form very uniform perovskite layer. But if we use the dual source evaporation process, we can form very uniform perovskite layer to construct the planar heterojunction device. So you can see that the thickness of the perovskite layer is around 500 to 600 nanometer, and it is sandwiched in between the planar titanium dioxide layer and the P-type hole transporting layer. So the charge should transport through the perovskite layer itself to reach at the selective charge transporting layer. So based on the planar heterojunction structure, they were able to achieve the efficiency as high as 15.4%. So at this stage, let us see the operation principle of the perovskite solar cells based on the device structure. So the typical device structure nowadays is this planar heterojunction structure, where the perovskite layer is sandwiched in between the hole transporting layer and the electron transporting layer. So the photogenerated electron is transported through the electron transporting layer, and the photogenerated hole is transported through the hole transporting layer. And here you can see that the device structure. So the electron transporting layer serves as a hole blocking layer, while it transports the electron, and hole transporting layer serves as a electron blocking layer, while it transports the photo-generated hole. So typically we call this charge transporting layer as a selective contact. And owing to the high absorption coefficient, the typical perovskite layer is around 500 to 1000 nanometer. And as you can see, the depletion region at the interfaces seems to be relatively thick, which means that the depletion layer is localized at each interfaces with selective contact. This is because the charge carriers in the perovskite material has very long diffusion lengths. So although the depletion region is not very thick, we can still collect the photo-generated charge from the bulk of the perovskite layer. For understanding of the structural stability of the perovskite material, we should understand the concept called tolerance factor. This tolerance factor describes the structural formability of the ABX three-dimensional perovskite materials. So this tolerance factor equation can be derived by the simple observation that this unit cell is the cube. So as we learned in the previous slide, in the ABX3 perovskite structure, the A cation occupies the cubo-octahedral site, and it is surrounded by BX6 octahedral. So if we assume that this unit cell is the cube, there should be the relationship between, for example, this length. So let's say this length is the L1, and this length L2, and this length L3. So if we assume that this unit cell is the cube, first the L1 should be the root 2 times L2, and this L2 should be same with the L3, right? And although we draw the crystal structure by using ball and stick model here, in fact, in real crystal, each ion should contact with the other ion, as you see in this figure. So we can in fact describe the L1 by using the ionic radius of the A cation and the X anion. So the L1 should be the distance between this point and this point. So the L1 can be written by using the ionic radius of the A cation and halide anion. So 2 times Ra plus Rx. And similarly, the L3 can be described by using the B cation and X anion. So L3 should be the twice times Rb plus Rx. So if we plug in this L3 and L1 here, then we can get the relationship between each ionic radius. So if I rewrite here twice times Ra plus Rx should be the root 2 times twice times Rb plus Rx. So we can remove the 2, and then if we assume that it is ideal cube, it should be the same. And then if we move this term to here, then root 2 times Rb plus Rx over Ra plus Rx equals 1. So you can see that this is correspond to the definition of the tolerance factor. So ideally, we should get the tolerance factor of 1 to form the cubic perovskite structure, but it can deviate from the 1 depending on the each ionic radius. So depending on the tolerance factor, so we can define this as the tolerance factor. So we can see that if this tolerance factor is from 0.9 to 1, we can form the cubic perovskite structure. But if the tolerance factor is deviate from the 1, if it is lower than 1 or higher than 1, it forms the distorted perovskite structure or non-perovskite hexagonal or other layered structure. And if we see the electronic band structure of this three-dimensional perovskite, this is the EK diagram. So the y-axis is the E and x-axis is the K. You can see that it is direct band gap material where the minimum and maximum of the conduction and valence band is at the same K point. And if we divide each molecular orbitals, you can see that this range is the band gap region. You can see that the conduction band and valence band maximum is mainly consist of the molecular orbital from the lead and the halide. In contrast to the lead and halide, the organic cation just contribute to the very deep state, which is not directly related to the band gap of the material. So it means that although we change the A cation, it should not directly contribute the band edge state, which is closely related to the charge carrier property of the perovskite material. And from the curvature of the band structure, we can calculate the effective mass of the charge, where both the electron and hole effective mass was calculated to be 0.1 to 0.2 of the electron mass. And the other characteristic property of this perovskite material is the defect tolerance property. For the case of conventional semiconductor, such as the CDSE and gallium arsenide, if we break the bond, which means that if we form the antibonding state, such antibonding where each molecular or atomic orbital tends to be formed at the band gap state, which can serve as the trap state to trap the charge carrier and reduce the charge carrier transporting properties. But for the case of perovskite material, because of their characteristic band structure, the antibonding state or the broken bond state is formed at the inside of the energy band or very close at the energy band. So although they form the defect state, it does not severely degrade the charge transporting properties because it is very shallow. Although charge carriers are trapped at the site, it can easily escape with small energy. such as the thermal energy at room temperature. So owing to this defect tolerant property, as we saw in the previous slide, charge carrier diffusion length of the perovskite material is superior to the conventional CIGS or gallium arsenide. And although the A site cation does not directly contribute to the band edge state, they indirectly contribute to the energy band state at the band edge by distorting the crystal structure. So depending on the size of the A cation occupying the cubo-octahedral site of the crystal, the surrounding arrangement of PBI6 or PBX6 octahedral can be changed, such as the bonding angle or bond length can be changed. So they can still indirectly affect the band edge structure, because depending on their geometry, the bond distance between PB and I and the bond angle will be changed, which will lead to the change in band edge structure. Band edge structure consists of the orbital from the lead and the halide. And so previously we saw that the tolerance factor should depending on the A site cation. So depending on the A site cation, the structural stability of the perovskite can be also changed. For example, if we use the different A site cation with different ionic radius, the tolerance factor of the perovskite material will be changed. And as we studied, ideally, if the tolerance factor fall in between the 0.9 to 1, they will form the perovskite structure at room temperature. But if the tolerance factor is too low or too high, they will not be able to form the stable perovskite structure at room temperature. And for the case of inorganic cation here, it is easy to calculate the ionic radius because they are usually the sphere. But for the case of organic cation, their structure is not centrosymmetry. For example, something like this. So it is difficult to calculate the radius of this organic cation. In this case, we can just assume that there is the rotational freedom, so it can easily rotate through all the axes. So we find the centry of the mass, and first, then find the atom which is most far from the centry of the mass. Then we can calculate the distance from the atom to the centry of the mass. So we can use it as the radius of organic cation. And in fact, for the case of the formamidinium lead triiodide, which is based on the formamidinium cation, here the Fa corresponds to the formamidinium cation. And for this formamidinium cation, if we calculate the tolerance factor, it is almost close to the 1. It is 0.99. So ideally, it should be able to form the ideal cubic perovskite structure at room temperature. But we should note that we only consider the size of the A cation for calculating geometric tolerance factor. But in fact, the rotational freedom and the symmetry of the cation and also the chemical bonding between the cation and the surrounding PbI6 octahedral should affect the real tolerance factor. So experimentally, this formamidinium lead triiodide cannot form the ideal cubic perovskite structure at room temperature. But if we heat the film at around 150 degrees C, it can convert into the cubic perovskite structure, which means that probably the effective tolerance factor is greater than 1. So we still require some energy to convert the hexagonal non-perovskite phase into the cubic perovskite phase. So at the temperature above some critical temperature, the cubic perovskite phase will be stabilized and the hexagonal phase will be converted into the cubic phase. But for this formamidinium perovskite, because of such metastable perovskite phase at room temperature, still the hexagonal non-perovskite phase was found to be more stable than the cubic perovskite phase. So it can easily convert it back to the non-perovskite phase. So this study calculates the energy barrier for the phase conversion, and it was found to be around 0.6 electron volt for the energy barrier between the hexagonal and the cubic perovskite phase. And because of such metastable perovskite phase, this cubic formamidinium perovskite film, although we form at the 150 degrees C, as we store this film under ambient condition or relatively higher humidity condition, it can easily convert it back to the hexagonal non-perovskite phase, which has the much higher band gap. So you can see that as the time goes by, the absorption property of the film severely degraded because of the phase conversion. And also from XRD, we can see that the peak originate from the hexagonal phase appear as the time goes by. And such metastable formamidinium perovskite phase, in fact, their stability can be enhanced by their tolerance factor. We can use allowing strategy. For example, if we incorporate some portion of cesium lead iodide, which has the tolerance factor of around 0.81, we can in fact decrease the tolerance factor of the formamidinium perovskite. For example, if we incorporate this cesium as much as 0.1, the effective tolerance factor should be calculated from this equation, 0.1 times 0.81 plus 0.9 times 0.99. So if we calculate this, we can get the tolerance factor of around 0.97, which is relatively lower than the pure formamidinium perovskite. So in principle, we should be able to reduce the volume of the lattice by incorporating smaller cesium cation. So in fact, if we incorporate the small amount, 10% of the cesium, you can see that peak in the X-ray diffraction pattern shift towards the higher angle, which means that the lattice constant should decrease. So you can see in this graph that the calculated lattice constant is in fact decreased from around 6.32 to 6.29, and the lattice volume consequently reduced as well. And from the XRD measurement, we can also see that in case of pure formamidinium perovskite, there is some residual hexagonal non-perovskite phase, although we heat the film at a high temperature. But for the case of formamidinium and cesium hybridized perovskite, we can see that it only consists of pure cubic perovskite phase. And from the DSC measurement, DSC TGA measurement, we can in fact observe the some endothermic or exothermic peak when the phase transition occur, because there is the energy transfer from the crystal. So for the case of pure formamidinium perovskite, there is some endothermic peak around 106.5 degrees C, which is originate from the phase transition. But such peak disappear if we incorporate the 10% cesium, which means that there is no phase transition in the film. And this lower temperature endothermic peak is from the evaporation of the solvent from the film. And from the photo of the film, you can already see that the color of the film with the cesium is black, which means that the perovskite phase is formed. And owing to the enhanced thermodynamic phase stability at room temperature, we can see that the film stability under high humidity and the sun illumination is improved with the incorporation of the cesium. So this is the absorption of the film at the high humidity and the sun illumination. And owing to the improved film stability, the device stability was also improved. You can see that this data is without encapsulation. You can see that the device efficiency stability is improved with the incorporation of the cesium. And also the device performance is higher with the incorporation of the cesium. In addition to the structural stability, recently it was found that the central A cation has a crucial role on determining the optoelectronic properties of the perovskite materials. As you see in this figure, the central A cation in the octahedral cage can freely rotate because of the weak hydrogen bonding with the surrounding PBI6 octahedral. From the NMR study, for example, methylammonium cation found to have the cation reorientation correlation times as fast as 100 picosecond, whereas that of formamidinium and guanidinium cation was found to be much faster than the methylammonium cation. Using the time-resolved optical curve effect measurement, once we excite the perovskite film with the light, in case of cesium lead bromide, there is very fast change in reflective index of the film, which is due to the response of the inorganic lattice to the exciting light. But in case of perovskite film with organic cation, there is additional change in reflective index with a slower time scale, which is originated from the reorientation of the organic molecules. This reorientation of A cation was found to induce the dipole like this. So this dipole can screening the electrostatic interaction between the photo-generated electron and hole, which reduce the probability of the charge recombination. So the quasi-particle, including the polarized lattice and the charge, this quasi-particle is defined as a polaron. And also, another researcher found that not only for the organic A cation, but also the inorganic lead halide cage can polarize in response to the photo-generated charge. So this kind of polaron can reduce the charge recombination probability to enhance the lifetime as well as the diffusion length of the photo-generated charge. For the case of halide anion, because the halide anion directly contribute to the band edge state, as we replace the halide anion, the band gap and the lattice parameter of the film significantly changed. So here the X indicate the fraction of the bromide. You can see that as we increase the fraction of the bromide in the film, the characteristic diffraction peak from the perovskite shift towards the higher angle, which means that the lattice constant is decreased. So the calculated lattice parameter is decreasing as we increase the bromide content. And as we decrease the lattice parameter, you can see that the band gap of the film gradually increases. So the color of the film is changed. This is because the bromide ion has relatively smaller ionic radius. Intuitively, we can think that as the ionic radius decrease, the overlap of the molecular orbital will become more significant. For example, for this case, it will form like this. But as we decrease the distance between two molecular orbitals, the overlap will become more significant to increase the band gap of the materials. And that is why the band gap of the perovskite film is increased with the incorporation of bromide ion. And you can see that as the band gap increase, the device shows the decrease in short circuit current and the increase in open circuit voltage. And as a result, there is some trade-off as we increase the bromide content. And you can see that with a certain amount of bromide incorporation, we can get the optimum power conversion efficiency. And the increased band gap can also be confirmed from the EQE spectrum. And in this figure, you can see that with the higher content of bromide, generally the humidity stability of the device is increased. This is probably because of the stronger electronegativity of the bromide, which will form the stronger chemical bonding with the central A cation, such that the reactivity of the perovskite films with the surrounding humidity is decreased. And the chloride ion will have the smaller ionic radius. So as we replace the bromide with the chloride ion, the band gap of the perovskite film will further increase. So you can see that from the bromide to the from the iodide to the bromide and chloride, the PL shift towards the blue region, which means that the band gap of the material is increased. So this kind of perovskite material can also be used for the fabrication of light emitting diode with the different color.